Okay, so in the last few classes, we were looking at our electromagnetic wave. And to be specific, we were looking at the transverse electromagnetic wave. So where we looked at how it is propagating in a lossless media and how it was propagating in a lossy media. So we looked at, how the propagation constant gamma came, which is made up of alpha and beta, where alpha is the attenuation constant and beta is the phase constant, right? So we looked at it and we did few examples on that. And then in the last class, we looked at our electromagnetic power, which is your Poynting vector. And we saw that how Poynting vector can be used to find the power density and the power which is carried by the electromagnetic wave. So in fact, we looked at the average Poynting vector expression and then how we can find the average power. So that was the last class. And we also saw, remember, that the power, it decays as a function of e power minus 2 alpha. That is, it decays double the rate, twice the rate compared to the amplitudes. So this was the quick review. Now, today we are going to look at the other aspect of our electromagnetic wave, which is transmission and reflection. So as I gave you a brief introduction in the last class, that we want to now see that we have our transverse electromagnetic wave. Again, in this case, we are going to take the TEM wave. So where you have an electric field component and a magnetic field component, they are traveling in air or in any medium. And for example, when it comes and hit a boundary, that means it is now moving from one medium to another medium. Then what happens to this electromagnetic wave? Of course, as I told you, logically, if you think that there should be a part of the amplitude of the electromagnetic wave that should be reflected and part should be transmitted. Or in other words, part of the power will be reflected and part of the power will be transmitted. Now, in today's class, we are trying to see how much is the amplitude reflected or how much is the amplitude transmitted. And then we can also find the power, how much is the power reflected and how much is the power transmitted. So that's the main objective of today's class. And now when it comes to the transmission and reflection, now we have to also define the boundary or the interface. How is the interface? So therefore, we categorize our analysis into two types. First is the normal incidence, which is the special case of this one, but it is easier for us to get a head start. So if you see here, this is my boundary and this is my boundary, which is normal. That means my electromagnetic field is hitting this boundary at 90 degrees. So if I draw the normal to this boundary, this is the dashed line, right? And this dashed line, this angle is 90 degrees. So that's why it is called as a normal incidence. So it will hit the boundary at 90 degrees. Then it can also hit the boundary at an angle. So if you see here, if this is my normal to the boundary, then if my electromagnetic wave hits like this, that means it is hitting at an angle, which is theta I. And therefore, you will also have some reflection and you will also have some transmission. So first we will look at the easier and the special case, and then we will move to this incidence. So this is called as normal incidence and this is called as oblique incidence. Okay. So in the normal incidence, if you see here, so this is my statement. So where I have two regions, as you can see. So this x-axis or the xy plane is my boundary. See, this is my boundary. So here you have medium 1, whose characteristics are epsilon 1, mu 1, and sigma 1. Medium 2, epsilon 2, mu 2, sigma. And here is my incident field. So this dotted arrow is telling me the angle. Okay, so let me make it a little bit small. This is too small. Okay, So if you see here, this is this dotted is my direction. So this is my direction of propagation of my incident field. This is after hitting the boundary, returning back, and some of the electric field, electromagnetic wave is transmitting in medium. Now, how is the electromagnetic wave? As you can see, this is my incident electric field. This is its direction. So it has only X component, and incident magnetic field whose direction is coming out of our screen. See here. So this is my Y, which are with a dot. So that means coming out of the screen. So this is my incident. So my transmitted will again be in this the same direction along the Z direction. Then this will be my transmitted electromagnetic wave, and this will be my transmitted transmitted electric field and the transmitted magnetic field. And the magnetic field direction is again coming out of the screen. Now, how about the reflected one? So in the reflected one, we know the arrow. Okay. So now what we are saying that, okay, so when this is reflected, then this is my reflected electric field. So my reflected electric field is still along the X direction. Now, based on your electric field and your direction, you need to find your magnetic field, because we know that E cross H will give me the direction of propagation, right? So if my reflected field, it has a component of AX, and my direction is what? Minus AZ, then my reflected field, reflected magnetic field direction will be what? Yes, Mr. Nawaf, can you tell me what will be its direction?
It will be in the positive Z.
Yeah, no, this is minus Z. So in order to complete this one, our electric field component is AX. My direction of propagation is minus AZ. See, it is going backwards. So that's why it is minus AZ.
Minus AY.
So it will be minus AY, right? So minus AY. So that's why if you see here, my reflected magnetic field has a cross mark here. Why? Because it is not coming out of the screen, but it is instead it is going into the screen. So this is the direction that we identified based on our reflected electromagnetic wave direction and my reflected electric field. Okay. So once we have formulated our electric field, our diagram, then what we are doing is we are now writing our expressions. And again, what we are doing, we are following the phasor notation. So what will be the incident electric field? So it is the EIS, S corresponds to the phasor, the direction is AX, and the incident field amplitude is EI0, e to the power of minus gamma 1Z, where gamma 1 is the propagation constant. So gamma 1 is what? Is the propagation constant. Propagation constant. Right? So this gamma 1 will be equal to alpha 1 plus J beta 1. And alpha 1 will be the attenuation constant of your medium 1. Beta 1 is the phase constant in medium 1. And now what will be my correspondingly or associated magnetic field? It is now AY, and the amplitude, they are related with the characteristic impedance. So that's why I am now saying, instead of writing HI0, I'm writing in terms of the amplitude of the electric field. So it is EI0 over eta 1. And what is my eta 1? My eta 1 is the characteristic impedance of my medium 1, which I can easily find as root of mu 1 over epsilon 1. Right? E power minus gamma 1Z as it is. So this is my incident electric and magnetic. Similarly, I can find the reflected electric and magnetic field. So what is my reflected electric field? ERS is again, it is AX direction. Now the reflected field will have some amplitude. That's why I'm representing it as ER0. And what will be the propagation constant? Because you are in medium 1, therefore it will still be, the propagation constant will be gamma 1. But now see here, guys, we do not have minus here. We have plus here. Why we have plus here? Yes, Mr. Talal Al-Jabr, can you tell me why we have plus here? Talal, you are there? Okay, it seems he is not there. Thabit, can you tell me? Thabit Al-Khahtani?
Yes, Dexter, I'm with you.
Yeah, can you tell me why we are writing plus gamma 1Z here?
Not sure, Dexter.
See, here we have minus gamma, but here we have plus gamma. Yes, Thabit, why? Try to link it from the wave propagation point of view, right? Try to link it from the wave propagation point of view. See, our incident field is moving in this direction, right? So what is this direction?
Plus Z.
Plus Z. So for plus Z, your beta or your gamma will become minus. Because when you find its instantaneous form, it will become cosine of minus gamma 1 Z omega T minus gamma 1 Z. That's why. So negative represents positive Z direction. Now, how is my reflected field? Is going in which direction?
And the minus Z.
Minus Z. So therefore, your gamma must be
Plus Z.
positive, because if I look at its instantaneous form, it will be cos of omega T plus gamma 1 Z. So that's why you have plus here. I hope it is clear now.
Yes, it's clear, Dexter. Thank you.
Welcome. Okay, so now let's continue. So therefore, you have your reflected magnetic field amplitude. We have already seen that its direction is into the screen. So it is minus AY. And then again, I'm writing in terms of the amplitude of my reflected electric field. So therefore, my reflected magnetic field amplitude is ER0 over eta 1 and e power plus gamma 1. So here also plus. This is in the reflected. Then we have in medium 2, we have the transmitted field. So my transmitted field is AX and its amplitude is ET0. And since the transmitted field is moving in the positive Z direction, see, it is moving in the positive Z direction. So therefore it is e power minus gamma 2Z. It is not gamma 1 here, gamma 2. Why? Because gamma 2 is because we are in this region. So this region you have gamma 2, which is alpha 2 plus J beta 2. And you have your magnetic field. ETS is AY ET0 over, this will be eta 2, e power minus gamma 2 T. And what is your eta 2? Is the characteristic impedance of your medium 2, mu 2 over epsilon. Okay, so this is how we got all our electric field expressions, which is the transmitter, sorry, the incident, the reflected, and the transmitted field. Okay, so now what we will do, now what next, we will look at the total fields, because now we want to apply boundary conditions. Remember, so this is a boundary. So therefore, we will apply the electric field and magnetic field boundary conditions here. Electric field vector, magnetic field vector boundary conditions. So first, let's find the total electric field and magnetic field here, total electric field and magnetic field here, and then we will apply the boundary conditions. So I know the incident, reflected, and transmitted field. So can I find the total field in region 1? So what will be the total field in region 1? What will be the total electric field in region 1? Yes. Mr. Ahmad Al-Ghamdi, are you there? No? Mr. Abdul Rahim Al-Mushrif?
Yes.
Yeah, so can you tell me what will be the total electric field in medium 1, Mr. Abdul Rahim?
It will be the incident and the reflected.
Reflected, yes. So you have to first add EI and ER. That will give me the total electric field in medium 1. Then you have to add HI and HR. That will be the total magnetic field in medium 1. Now, what will be the total electric field in medium 2? Because you do not have any other electric field except ET. So therefore, ET will become the total electric field in medium 2. And similarly, HT will become the total electric field in medium. So therefore, if you see here, the total electric field in medium 1, is nothing but the incident electric field and the reflected electric field, which is this one. And the magnetic field, incident magnetic field plus reflected magnetic field, which is this one. And the total field in region 2, E2S, is only the transmitted electric field, and H2S is only the transmitted magnetic. So therefore, now we have the complete electric field vector in medium 1, complete magnetic field vector in medium 2, in medium 1, and the complete electric field vector in medium 2, and the complete magnetic field vector in medium 2. Now let's go and apply the boundary conditions. So now what boundary conditions you are applying? Because my interface is charge free, there is no charges, because we started our electromagnetic wave derivation assuming that there are no charges, that there are no sources. So rho v is 0 and there is no surface current. So therefore my boundary is charge free and current free. And in that case, now I'm applying the boundary conditions. So what is the boundary conditions? The boundary condition says if rho v is 0, that which is there is no charges and there is no surface current, then the tangential component of electric field and also the tangential component of magnetic field will be continuous. Okay. So, and it will be continuous where? It will be continuous at the boundary. So now where is our boundary situated? My boundary is situated at x is equal to 0, right? At x is equal, not x is equal to 0, sorry, at z is equal to 0, right? So therefore, the boundary condition says that the electric field tangential component and the electric field tangential component in medium 1, in medium 2 must be equal at the interface. That means at z is equal to 0. And why I'm saying E1s and E2s directly? Because if you see here, your E1s is made up of x component and your E2s is also made up of x component. And if you see here, your x component is what? Your x component is this. And therefore, your x component is nothing but your tangential component, because this is my interface. This is my boundary. So it is tangential to the boundary. That's why. And in the same way, your magnetic field vectors will also be tangential to the boundary, because your magnetic field vector is what? It is these ones, which are this, coming out of the boundary and going inside, out of the screen, going inside the screen. But still, they are tangential, because now if you think it in 3D, so this will be my interface. Okay, sorry. So this will be the x direction and this will be the y direction. So therefore, I have an electric field, which is HI is in this direction, and I have an magnetic the magnetic field HI in this direction and the electric field EI in this direction. See, both of them are residing on the XY plane. That means they are residing on the boundary. They're staying in the boundary. That's why both of them are tangential components. And that's with this, we go and we substitute the expressions. And when we substitute the expressions, so at z is equal to 0, so substitute z is equal to 0 here. So e power minus 0 is 1, e power minus 0 is 1. So all the exponential terms will go away. and therefore I will get as EI0 plus ER0 is equal to ET0, and EI0 over eta1 minus ER0 over eta2 is equal to ET0 over eta2. So this is when applying the boundary condition for the electric field. This is when applying the boundary condition for magnetic. And now with these two equations, we can find the relationship, because what is known to us, the incident electric field is known to us. That means the incident electric field amplitude and the incident magnetic field amplitude is known to us. Now we can find the reflected amplitudes and the transmitted amplitudes. So just manipulating this, we can express the reflected electric field amplitude in terms of the incident field amplitude and the transmitted field amplitude in terms of the incident, which is ER0 is eta2 minus eta1 over eta2 plus eta1 times EI0, and ET0 is 2 eta2 over eta1 plus eta2 EI. And what is this terms called? So this term for the reflection part, that the reflected electric field and the incident electric field relationship, this is called as reflection coefficient, gamma, uppercase gamma, which is nothing but the ratio of the reflected field amplitude over the incident field amplitude, which is eta2 minus eta1 over eta2 plus eta. This is called as the reflection coefficient. Similarly, this one is called as the transmission coefficient. So transmission coefficient, guys, you know, in the book, we usually used tau, okay, and reflection coefficient is uppercase gamma. But in my notes, I'm using capital T just to, you know, make it much clearly visible. So it they are the same. Okay, so this is how you can find the amplitudes. Okay, so now let us first talk about this example, and this example is telling now that my medium 1 is a dielectric, but my medium 2 is a perfect conductor. Perfect conductor. That means, you know, you can think it like a metal. Okay, so air metal interface, metal, because, you know, you can go for steel and copper, any metal, although they are not perfect conductors, but let's assume them to be a perfect conductor. Then what will happen? So your electromagnetic wave is coming and hitting a perfect conductor. Then what will happen? Will the electric field go inside this perfect conductor or not? So what do you expect? Yes, what do you expect? Because we have seen the properties of a conductor in the electrostatics. So what do you expect? Do you expect the electric field, transmitted electric field, to be there? Yes.
No.
No, it will not be there. You're right. Because the electric field cannot exist inside the conductor, because this conductor is not conducting. Therefore, let's check here. Now, what I'm doing here, I'm now finding, because now I'm everything, if you see here, they are based, the reflection and the transmission is based on only the characteristic impedance. So I can generalize and say that it's the characteristic impedance which defines how much amount of electric field amplitude will be reflected and how much amount of electric field amplitude will be transmitted. So it's just the characteristic impedance between these two materials that will decide. So therefore, what I'm doing here, I'm finding the characteristic impedance of medium 1, which is a dielectric, root of mu1 over epsilon 1. I'm finding for medium 2, which is eta 2, which is root of mu2 over. So now I'm writing as for a conductor. And then since it's a perfect conductor, right? It's a perfect conductor. That means its conductivity should go to infinity. So if the conductivity goes to infinity, then the characteristic impedance of our perfect conductor, this term, if goes to infinity, then my eta 2 goes to 0. In that case, what will be the reflection coefficient? If you substitute here, the reflection coefficient will be -1. And the transmission coefficient tau will be 0. So what does this tell us? If the reflection coefficient is -1, what does this mean? It means that the complete electric field amplitude or the magnetic field amplitude is reflected back. And tau is 0. Transmission coefficient is 0. That means there is no electric field which can be transmitted. So there is no transmitted electric field existing in the perfect conductor. Okay, which is correct, which is consistent with what we have studied in our electrostatic. So that's why no transmitted field occurs in the perfect conductor and all the incident electric field is reflected. Okay. Then here we are now again going a little bit to the next example, and we are now trying to see that if complete electric field is reflecting back, or our complete electromagnetic wave is reflecting back, that means what is happening in our medium 1, which has the incident field also, incident electromagnetic wave also, and the reflected electromagnetic waves also, and both are of the same amplitude, right? But yes, one is returning back, so one is traveling in the -z direction, and the incident is traveling in the +z direction, and both are of equal amplitudes. Then what's going to happen in this medium 1? This is what we are trying to see in this example. That again, you are taking a dielectric with a perfect conductor, and now we are looking at the field expressions. So we want to find the field expressions in dielectric, which is E1s in air, because my medium 1 is air and my medium 2 is perfect conductor. See, medium 1 is air and medium 2 is perfect conductor. And this is the electric field, which is incident normally to this interface. And my incident electric field is EIS AX EI0 e power -j beta 1x. So I'm now not using gamma 1 here, I'm using beta 1. So when I'm using beta 1 here, that means automatically it means that my dielectric, which is the air interface, I'm assuming it as lossless. That's why there is no alpha. Okay, so now my E1s, that means my total electric field in air, total magnetic field in air, and total electric field in conductor, and total magnetic field in conductor. This is what we need to find. So let's start. So the total, this is my incident, right? So my total reflected field will be AX ER0, AX ER0 e power -j ER0, this is the reflected field amplitude, and then e power j beta 1x plus j, okay? Because guys, here I'm not using gamma, I'm using beta. So that's why j must be there, because remember, gamma is alpha plus j beta. So when my alpha is 0, then my gamma should be replaced by j beta. This we have seen it in our previous class. So that's why it is plus j beta 1z, because it is going in the -z direction. This is the -z direction. So therefore plus. Now ER0 is what? Gamma EI0. I'm replacing it with the reflection coefficient times the incident field amplitude. And what is the reflection coefficient? Just now we calculated the reflection coefficient for this case. It is -1. Got it? So this is my reflected field expression. And therefore my total electric field will be the incident plus reflected. So the incident plus reflected. Okay. And then if you see here, there is a minus here. And if you see, if you take AX and EI0 common, this is e power -j beta 1z minus e power j beta 1z. And this from our complex numbers, we can replace it with sine. So it is nothing but minus 2j ax ei0 sine beta 1 z. So this is what I'm seeing as my total reflected field. Now, in a similar way, if I do it for the magnetic field, the total magnetic field, then I will get the total magnetic field as, if I do it, I will get the total magnetic field in air as AY 2 EI0 over eta 1 cos of beta 1 Z. Cos of beta 1 Z. So that means what is happening? Along with the amplitude, there is a term coming, which is a sine term in the electric field or a cos term in the magnetic field. That means my electric field and magnetic field are 90 degrees out of phase, and they are a function of Z. They are a function of Z. Then, what is the total field in the conductor? We know it. They are 0. Now we need to find the instantaneous form. So let's find the instantaneous form of this and the instantaneous form of this. So the instantaneous form of E1 is real part of this, which will be AX 2 EI0 sine beta 1 Z sine omega t, because J is there, that's why sine omega t. And H1 is cos of B1Z cos omega. So now when you look at this, you see that the result of the incident and the completely reflected wave forms a standing wave pattern. So you are, if you see this in the in a say video, what you will see, you will see that, you know, they that means the superposition of the electric fields, both, or the superposed magnetic field will form a sine wave standing pattern, as if just the electric field is just, you know, dancing. That means you will not be able to see the propagating sine wave. You will see a stationary sine wave and it will be dancing. That is called as the standing wave pattern. So you will see that as if it is just standing, it is not propagating. And why this is happening? Because you are getting the superposition of the electric field incident and the reflected. Okay. And if you want to see this further, I brought this examples for you. So if you see this example, this is what I wanted to show. So show you. Okay. So if you see here, so this is my TEM wave, right? This is my TEM wave. This is my electric field. Let us assume that this is my red is my electric field and blue is my magnetic field. This is my transverse electromagnetic wave. And let us assume that this gray is my conductor. So what will happen? Let's see. It is propagating and now it is completely reflecting back, both. And after some time, okay, now can you notice our electric field and magnetic field now? Are you able to you know, see whether, you know, whether are you able to see my sine waves traveling now? No. See here, they are just dancing. Again, can you see them traveling? Because see here, you are able to see them traveling, but after some time you get the reflected field and both are getting added, and now you don't see them traveling, you just see them dancing. See, you just see them dancing, and this is nothing but your standing wave. So you will no longer see them moving, you no longer see them propagating, because the propagation in the positive Z direction and the propagation in the negative Z direction, they are adding in such a way that your overall electric field and the overall magnetic field is like dancing. Clear? So this is the thing. See, it will be dancing. So this is called as the standing wave pattern. Okay. And this is another nice example where, it is not, so this is my interface, but this is not a conductor. It is some interface with some medium. And in that case, you will see, how the transmitted field will be, you will see a part of them reflected back and the part of them transmitted. When the part of them is reflected back, then the superposition of the reflected field and the incident field will again form a sort of standing wave pattern, but it will not be a perfect one. It will not be a perfect one. That means it will be moving, but you will not be able to see. So this will be the transmitted. And here, I'm sorry, and here you will see both the incident and the reflection. Okay. So these are some of the animations which I wanted to show you for the incident and the transmitted field. And these are all normal incidents. So let's come back. Let us take one more example. With that, maybe we will stop for our quiz. We will take one more example. Yes, I know. We will quiz. Oh, okay. Okay, I think we will stop here because we may not have enough time to take the quiz. So, okay, guys, please be ready. Open your cameras and just arrange yourself quick.
Doctor, the quiz will be in